Welcome. In the world of chip design, ensuring speed and functionality is paramount. This session delves into static timing analysis, a critical technique for verifying, timing performance in integrated circuits. We will explore the importance, the tool used, the steps involved in performing STA for optimal design. STA is a key to high performance designs. Let's get the context of what we're talking here, right? It said, anything we design, it has to be verified. Okay, that's a minimum expectation requirement. So now we are designing SOCs or a complex ICs. Okay, and we have to verify thoroughly. Okay, we can broadly classify verification in this context. The verification against foundry requirements, for example, DRCs, etc., and verification against required functionality. For example, you do schematic simulations and verify your design against specs, for example, gain, bandwidth, speed, etc., right, the delays, etc. And we do RTL simulations and check where functionality is proper and as per your requirements, RTL verification, right? So at the same time, we also have verification against required performance. Okay, your functionality is good. What if it's not meeting the timing expectations, right? Your delay is too much, or your bandwidth is not enough, right? So timing verification. So timing verification is integral part of ASIC design flow. We cannot afford to compromise the time. Okay, it's important. Now, how do we check the timing question, right? Typically, the legacy thing is like if our designs used to be very small and we used to go with dynamic simulation, like you keep changing input vectors dynamically and see output, uh, how outputs are coming and you see the functionality same, right? So timing also done in a similar way. What is the delay? 50% to 50%, 10 to 90% delay, all those stuff, right? It's just what we use is typically we use Spectre models or spice level models. Look at the the one of the equation for drain current here in the lower technology nodes. We used to have square law, hardly few components, the variables in the drain current. Right now, look at the current. There's like literally more than 10, right? So and it's more also. Okay, so now we have billions of transistors and using such a complex formula and solving these equations for billion of transistors, it will not work out. It's simply impractical for a full chip verification, right? So naturally dynamic simulation is not the way to go ahead, right? It is much slower and it's impossible for full chip, right? So then what's that? Then we have to verify timing. It's important for a full chip. Otherwise, we are taking huge risk, and your chip will definitely fail. It's such a complex, right? Then what is solution is you break the designs into many timing paths. Okay. Then calculate the signal propagation delay along each path and check for violations. Small paths and do it. Compute and check the violation. While doing this, don't do simulations, don't do dynamic, use lookup tables. Lookup tables are pre-computed values stored in table format, in a matrix format. So the beauty here, look at it, its simulation is not involved. Okay, the spice levels are not required. Okay, and since it is typically a mathematical, or simply you can say I can simplify it as an addition of delays in series. It's much faster compared to dynamic timing analysis. Observe this. We have a single inverter. Okay, there's a single input pin and output pin is single. Okay. Now, what are the input combinations possible? 0 and 1, 2. So we do simulations and we get to see that some X time, right? Now I'm considering the same, inverter, of course, with control circuitry. So inputs have become 2, output is 1, right? So there's a look at the overall combinations. Okay, and this time I'm considering not just 0 and 1, but also high impedance state Z, of course, and unknown state X. Okay, input can be whatever state, right? We don't. Okay. So if I consider all those things, the overall possible combinations, look at it here for a this inverter is 16. So if I do dynamic simulations, it takes much more time than the simple input inverter. Now onwards, let's not worry about Z and X because we need to consider in the simulations just for discussion. 2 input NAND, we have got 4 gates, 4 possible states. For 3 input, only one input is increased. We have got 8 states. Now it is 4 2 to the power of, you see it's increasing 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Literally, it's in the order of 2, it's increasing. Okay. So now 4 inputs, we have got 2 to the power of 16, possible combinations. And imagine doing dynamic simulation for all these things. It takes time. Okay. So here look at it, number of inputs are huge and it takes more time. See, when it comes to complex chip, right, so our inputs are like not in 10, not in 20, it's like hundreds and hundreds possible combinations, literally thousands of combinations, right? So we cannot afford to do spice level simulations for such a complex design. It takes huge time. Okay, first of all, design itself is not possible, not it, like you need to be a genius to do it in time, for these things, right? So why these days there are a lot of advancements in the computer or computing technology, right? So we can use the power of the computers to synthesize and create such circuits as per our inputs given in the form of RTL. Okay, so the tools can do such a complex circuit design, synthesize basically, then but it has to be verified, right? Then so that methodology also has to be automated, simplified. That's how we are coming with STA, simplified and faster methodology to verify such a complex circuit synthesized by the tool. Okay, okay, these are some of the examples I just captured. We'll talk about it later. And to summarize and to make it very clear, STA does not verify functionality. It does only the timing. Okay, verification. Okay. So now dynamic simulations are very slow. We learned it, right? So gate level simulations and space level simulations both are dynamic simulations. Space level simulations uses physics models and the present day physics models for, say for example, drain current of a MOSFET is like very complex. Imagine using such a complex formula for billions of transistors. Doesn't make any sense to at chip level. It's literally unrealistic. But when it comes to gate level, though it will not use spice level simulations, I mean like sorry, spice models, such a complex formulas, but still it is structural design. Okay, and we have millions and millions of gates interconnected in a structural way, and your signal pass has to pass through such a complex path, right? So even gate level simulation is not that realistic at full chip level, though it is faster than spice level simulations. Okay, then we know now both taking a lot of time. One is unrealistic, one is too much slow. So what is the solution? We have to find a solution for calculating the delay or computing the delay. Then that method is lookup table method. Okay, so in this lookup table method, the delay calculation is simply a problem of addition. Okay, it's an addition. Your present day computers are much faster, stronger. Computing power is very high. They can do this addition even for a millions of additions. You can do it quickly. Okay, so much faster. So let's see how this problem of dynamic simulations using spectral spice models physics formulas turned out to be addition problem. Okay, observe this problem. So assume this is a I'm interested in calculating the delay from this path to this path. This is a flop and this is data pin and this is clock pin. Okay, from here to here. Now we have a lookup table, we call it as .libs or liberty files, that has this delay numbers and this the numbers, all these delay numbers of each cells are captured and recorded in the matrix format. Okay, so now when I calculate when I'm doing STA, what I simply do is I add, because these are on series, I simply add the delays from all these 4 cells. Of course net delays also getting added. So the problem is now simply addition of 4 delays plus 4 cell delays plus 4 net delays. Okay, right, now verification has become so simple. A computer delay and we have a says assume we're worried about setup time. So setup time, we need this data to appear here at least one setup time earlier than this clock, right? So if it comes late, oh, it's violated, we fix it. If it comes before that one setup time. So our design is working good, great. Okay, and we make a decision here. So we are able to come up with a decision much earlier. The reason is we are able to compute the delays faster. That's how we do it. Okay, so many a times the present day tools are so powerful that assume for a moment this data is getting delayed a lot. It's coming later than one setup time from the clock. For example, this is the clock. Okay, I'm supposed to come here, but this is setup time. This is setup time. Okay, this is setup time, for example, but it's coming late. What it does is it's delayed, right? Delayed. So what it does is the tools are capable of calculating the delay and replace this gate with faster gate, reducing, making it 3. So reducing the overall delay from here while meeting the setup time of it. That's the beauty of present day, uh, the tools. Okay. This is done, right? So now, okay, then what is the meaning of it? Let's see that. Static means, it's not dynamic, it's not changing, it's static, right? Either 0 or 1. That's how we do it. Okay. Inputs are not really toggled at the input. Here, it's not either it is 0 or 1. It's not really toggled here. Okay. And what is timing? So we compute the timing. What do you mean by computing here? It's not like solving big complex form, the matrices or physics formulas. It's simply addition, as simple as that. Computation of delays. And once you compute, you analyze the time delay, which check whether it is acceptable range or not change. If it is not in acceptable range, then fix the design. Otherwise, move on. Okay. So now it's very clear. Okay, what are the checks it does, right? I've just captured a couple of things here. For example, the kind of a checks it does, between synchronous check clocks, for example, is it checks for setup, hold, recovery constraints, minimum period, minimum pulse width for clocks. Okay, if the design rules checked are maximum transition time, minimum capacitance, max fan out. So many things it checks, and I'm just listing few things here. Okay, this is fine. Yeah. Okay. To summarize, one line, STA is significantly faster than gate level simulations, and it is many orders of magnitude faster than transistor level simulations. Okay, that's the advantage of STA. Okay, let's close it by definition. What is definition? STA, static timing analysis, is the process of adding the cell and net delays. It's a process of adding the cell and net delays to obtain the path delays and comparing the path delays to the timing specification to check whether it's meeting or not meeting. Here I captured a couple of waveforms which will help us to visualize, say, rise time. Here 10% to 90% time required, say, and delay from here to here, fall delay, output is falling, time required for input is changing to output falling, time required, rise delay, for example, here. So time required for this TPLH, and at the same time, this will help us to visualize what is setup time and hold time. Okay, so data has to be stable so that flop captures it and transfers to the output, and even after changing, data should not change. When data the flop captures the data, but input should not change. Data should remain as it is. This is a hold time here, and this is setup time here. Okay. In the right side, the computation using STA tool, these are all, the left portions are coming from the datlib files for individual cells. This is for a flop. This could be for clock root delay also. It could be for combination logic also in this scene matter. Okay. In the right side, the values captured in the computational table are added here or extracted here. For example, the STA tool goes to the liberty file, gets the delay for this, gets the delay for this, all those stuff, and of course it also adds net delays here and adds all of them. The overall delay is this much. Okay. Similarly, when it comes to flops, that actually, though this data is supposed to come here, what really matters, the time required for data to come here is not really this data to queue delay. This is the delay. For example, this clock to queue delay plus this combination inverter delay. Okay, that much time this data takes to come here. Of course, this clock takes this much time here to come here. Now see this data coming here. and this clock is coming here. Again, I should be careful about setup time and hold time here. Otherwise, this flop may read a wrong data. It might read a future data or a past data rather than reading the present data. Now let's understand where STA fits in the SOC design flow. Okay, so how it does is, we specify, a circuit functionality and the timing libraries. We capture RTL and write constraints. Okay, so we perform, synthesis. Of course, it is required to do it, convert RTL to gate level netlist while meeting timing constraints. It means it's used here. While doing synthesis, we use STA. Why STA? Keep timing in mind while converting your RTL, a Verilog code, a system Verilog code, to actual gate level netlist, a design. And once it is synthesized, we run STA again to verify the timing of synthesized results. Do the proper of this is post synthesis. We perform placement and routing, PNR or APR, automatic placement and routing, which is also called as physical design. So the timing driven PNR uses STA to meet specific. Again here we use it. Okay. Once the PNR is done, placement and routing is done. Okay. Again we run STA for final verification using sign off STA tool. This is where we sign it off. Sign off. At this stage, PNR stage, we keep doing experiments, trial and error. We do a PNR placement and route, check the timing. If it is violated, change the placements, optimize the delays by using proper buffers or inserting buffers or changing the way you route it. Okay. To summarize, we use STA within the synthesis, after synthesis, and after place and route. These are the 3 times or 4 times we use STA. So we also, okay, fine. Now here, right, let's understand what are the industry standard EDA tools for STA, right? So we have got 2 big players here, Synopsys, PrimeTime from Synopsys, one the well adapted tool by the whole image industry. And the other one is Tempus timing sign-off solution from Cadence. Okay, so just if I talk about the Tempus itself, right, it is it is timing engines are built into synthesis and PNR tools. For example, in Genesis synthesis tool for them, right? So it has got a timing engine built into it, and knows which is a the PD, at PD level Tempus is built into it, right? So it helps, the keep, while doing design, say synthesizing or, doing a physical design, keep timing in mind and take both of them together. Okay, that's how the integration plan. What these tools does is they do static timing analysis. They're used for timing closure and signing off your design timing. Okay, so uh, this STA is run at the gate level after design transformations. Gate level, right? Okay, that is after synthesis. You can say that after synthesis, of course, after PD, both are synthesis level after synthesis. So we need to run STA whenever there is a change in design netlist or design constraints. Okay. When it comes to design methodologies, right, we have broadly 3 types. One is a full custom design, the way we do it in analog design, like all takes MOSFETs, custom connect them and do it. Okay. Other one is programmable way. Okay, like FPGAs, what we do, we write Verilog system Verilog code, code for a given hardware and dump it, synthesize it, dump it there. Kind of a programming, right? Programming in off-the-shelf chip. Okay, FPGA. But both have their own advantage and disadvantage also. So the best of the both worlds is cell-based designs. It's a middle path between them, right? So we call that a cell-based design. Cells can be standard cells, cells can be macros like LDOs, PLLs, ADCs, etc., etc. Okay. So when it comes to cell-based design, what is the way is RTL? RTL design starts with RTL design. Okay. So what is RTL? RTL is register transfer logic. The idea behind this is, instead of writing a purely a behavioral code which may not be, which we tool may not fail to convert into hardware. Okay, what we do is at the end hardware is a goal, right? So we can go with structural design, connect everyone manually, NAND or thousands of NAND gate, connect them to it, which is time consuming. If it's complex, it's impossible also. And if it is purely a behavioral tool may fail to convert into hardware, we find a middle path again, RTL. Okay, so what is this RTL? Is register transfer logic. The idea behind is we have a registers. See, we are defining hardware here, okay, but not the entire micro connections. Okay, we are only defining number of hardware registers. For example, take 12, take 16, 0 to 16, right? And then we come up with a FSM or some logic. We say that transfer the data from this register to that register under so and so conditions. Okay, this is how register transfer logic is. It's a middle path. We are defining hardware, but we are not really structural in nature. Okay, it is behavioral in nature, not, but still it is a hardware component built into it. Number of registers are defined and the flow is defined. Okay, so now we understood registers were very, very critical for this flow. Okay, then what are registers? Registers which registers the data, which stores the data, and we generally latches and flaps are the one which stores it. Flaps are very important here. Let's store that. Okay, so that's the reason we need to understand what is flap here. At least 2 minutes here. Flip-flop is a storage device that is age triggered. Of course, we have level triggered. We cannot, it's transparent. We cannot store and transfer the data. We cannot track the flow of data, right? So we always go for age triggered, either positive or negative, doesn't matter. It's also commonly referred as flop or register. So this is an example of it. We have a clock here and we have a data here. See, whenever data changes, output data will not come here. For example, see, data is changing here. See, it's not changing here. Data is changing here only in the rising edge of the clock. It means this data is coming here and clock is controlled. The clock is like a door. It opens the door. It's coming. The data is coming and sitting in the door, and clock opens the door, and then this data comes here. Okay, so it means for every rising edge data at the input comes to the output at Q. Okay, this is the way to track it. The analogy is this clock can be we can have a very good analogy with the time with this clock. That's how the word clock is used here as well. The way you define the timings inside our chips using clock, especially that what made it possible is flip-flops, edge triggered flip-flops. Okay, right. So what really matters here is clock to Q delay. Here, this delay is what really matters rather than data to Q delay. Okay, there are two essential locks here: data to Q, clock to Q. What really matters is this delay. Okay. Okay. So what are the timing important parameters here? We have a clock to Q delay. This delay is important here, and setup time is important here, and hold time is important here. Okay. What are those things? We'll see it later. So these are the content from .lips. Okay, so look at it. Rise, for example, the setup rising. Okay, setup rising. Okay, so and we have old rising. Okay, so for different constraints. Okay, index 1, index 2. We'll see it later. With timing paths. Okay, I just took one of the image from one of the the tool provided itself for our analysis understanding. Okay, what is the timing path here? Is the timing path is a combination of all the timing arcs from a start point to the end point. See, this is start point. All the these are the start points, and these are end points. This and these are end points. So assume from here. Say this also. This is one positive path here, and this path. It went here, right? These are all the combination of all these timing arcs are timing paths. Okay. So these timing paths are classified majorly into 4 types. What are those? Are input to register. See, these are input, for example. Okay, input, and these are register means flops, remember. Okay, so from here this to this color is right. For example, this delay plus this delay is input to register need in. Okay, so now this delay we need a input delay at port. Data arrival time is we should know what's happening here, and then we can compute it here. Okay, this is input to register. Similarly, we have a register to output. For example, this is a register, right? This is a register. Okay, from this register to the output. So this delay is okay. Okay, but because this to calculate this delay, we need to understand this delay also, output delay also required. This then total is this clock to queue delay plus this delay is gives you the register to output delay. Okay, and input to output also. Look at this image here. There are no clock paths here or flip-flops here, right? So simply addition of this thing, this delay plus this delay. Of course, the delays to be added. So now to synchronize with other clocks, we should have a concept of clock or a virtual clock. We can use it here, or we need budget because there is no clock here. Because we define time inside the chips using clocks. Okay, so we should have a we should budget the timing here because we don't have a clocks here. Similarly, one more register to register. For example, this is a register and this is a register. And what is this delay is about? Okay, okay, that's the delay. So we use we use clocks at both input side as well as output side because we have clocks. It's good. We know how to calculate the timings. We have to understand the timings inside it. So to summarize, there might be multiple paths between the same port point the endpoints. From this point to this point, there can be one path can exist this way, one path can exist this way. From same start point to end point, there can be multiple paths. So, and each path is timed separately by STA tool to determine worst path. They calculate all and take the worst of it. Okay. Then it is also used to verify setup and hold time requirements for any capture flops in the path. Okay, one it takes the worst and the best, and based on that, it uses for setup time and hold time. I thought I'll list some of the timing checks we perform on a given design, and this design is again, and this circuit again is taken from one of the EDA vendor. Okay, so we can broadly classify them. Timing checks can be the one which is specified by the user, and of course which is specified by the vendor. But look at the left side. Most of our timing checks are setup and hold based. Okay, right side also we have a recovery removal, setup hold, max queue. The colors are anyway marked here, right? The different colors are there. Okay, it's only for reference. Let's understand the flow, timing analysis flow using PrimeTime, which is from Synopsys, which is widely adopted tool across industry. It has got 3 steps mainly. So what first step is, you load the inputs. Inputs can be your netlist, your parasitics, your constraints, so many things. Of course, once you load, you need to verify it. Remember, check, see whether all the things are good. Okay. Step 2 is, once that is done, you update timing. You generate reports. Okay. And once you generate reports, of course, you have to check manually and fix any errors are there. Okay, once all good are there, it's a iteration process anyway. Once all are good, you sign it off. Okay, you can also save your session in between and reopen sometime later. Okay, so now let's get into some of the scripting or command level. For example, I mentioned, right, step 1 is read the inputs, right? So inputs means what netlist, also gate level netlist is also input, right? So how do you read it? So that you use a PT shell, the PrimeTime shell. It's all written in a PrimeTime shell. Say current underscore design, that will read the gate level netlist. Okay, so for example, if you want to list the designs loaded in memory, okay, say get underscore designs. Okay, of star means list all things. Okay, so then at the same time, if you you can yeah, list underscore designs will source file name of the current design. For example, what is the file name which containing the present design which we are talking about. Okay, so typically your gate level netlist, which is coming from after synthesis. See, we do STA after synthesis, correct? So it means we need a gate level netlist. So this is generally coming from say design component level for STA. So now coming to the second step. For example, we read the gate level netlist, we printed them, we listed them. all good. Okay, then go to and load the libraries and set them properly, right? For example, you can set search path instead of every time writing the full path. You can set search path, right? And it, let's for example, from current directory, your reference library, it contains all the libs. Okay. Similarly, you can set the variable link path for the DB. Okay, designs to be initiated in the top level stage. For example, how is that? Set link path. Star. Your DB. And your standstill DB or IODB or any other particular design. Design DB. And then once it is set, right? These are the path setting and linking. Then you link the design. Okay, once the paths are set, you link the design. Okay, load the designs, set them, right? Done. Then third step, right? Once we read the gate level netlist, we loaded the libraries. Of course, wherever read the load, we checked it. Okay, then you have to check, one and two, right? How do you check? List underscore libs. Okay, it will list all, the libraries loaded. Print where link path, for example, this will, the link path will be printed. Okay, right, and search path is printed, all the stuff, right? So this is some of the comments which I'm listing, which are going to be useful when we really get into the STA using PrimeTime. These are PrimeTime commands. Okay, great. We read the gate level list. We loaded the libraries. Libraries means .libs and .dbs. Okay. For every design, and now we have to read the parasitics also. Parasitics, for example, if you are doing the STA along with PD or STA along with post PD, right? We need to have the extracted net list, for example, SPEF, standard parasitic extraction format, right? So those parasitics has to be read. Now how do you read? So read underscore parasitics minus format SPEF. Okay, where design data SPEF is your extracted net list in a SPEF format. We're done here, right? So then all three things are read. Then what is this? We have to, once read parasitics, we print the parasitics. I check the parasitics, right? How do you do? Report annotated parasitics in a PT shell. So it will, what it does is it lists total, the total lumped RC RC network and not annotated parasitics info for each of the internal nets as well as bound report nets, right? So of course, the RC values, comes from a SPEF. It lists, what this command will list the different parasitics. Okay, so once it is listed, we have to source the constraints. How do you source the constraint? Read underscore stc minus the code, of course, dollar constraint file. Constraint file typically .stc file. Okay, so and similarly source minus echo dollar constraint file. It source. So this is a tool generated file, but it agrees with the TCL syntax. Okay, so now it's very clear. Okay, check, of course you sourced it, then check the correctness of it. These are a couple of commands. Check underscore timing minus verbose. It will examine the design constraints. Similarly, couple of events, I'm mentioning it here. Use them. We can use them, right? So continue. Once now we have loaded the inputs, and we have to now generate the reports. Okay, we call it as updating. Okay, update timing. Okay, second step. Okay, let's talk about second. So how do you update timing? See, the first step is we have to update the timing. The commands are update underscore timing. You can do update underscore timing minus full. Minus full takes some more time. It completely does it. Okay, for all the things. So step 2B is once we updated timing, now we have to generate summary reports and check reports and results, right? So how do you generate and check? So of course you have to report underscore global underscore timing minus PBA. So they are different, we have a, the graphical based and we are a path based, analysis. Okay, PBA and GBA, right? So you can use minus PBA, path based analysis. Okay, report minus QR, the quality of records report you can generate for each path in the design, because it's a minus PVA each path, right? Timing and DRC violations in the design, it lists. Okay, report underscore constraints minus all violations, it lists. Okay, report underscore analysis minus coverage, report underscore global underscore slack. These are the detailed general, summary reports you can do. You can generate. Okay, so then you see it's generated, you have to analyze it, right? So how do you do that? So report underscore analysis underscore coverage. Okay, what it does is, it does a channel sanity check, lists the checks under, met, violated, and untested. You can see that really, okay, what are the checks which are met? Great, close it. What are the checks violated? Go and fix it. And it also lists the things which, tests which are not tested, untested. Okay. So, for example, what are typical tests it does is, it does setup, hold, recovery, removal, minimum period, minimum pulse width of a clock, and clock gating setup, clock gating hold, out setup, out means so many things it will check, and I'm talking with respect to particular design. Okay, then we are done. We updated the timing, we generated the summary reports, we analyzed the coverage analysis. Then what is that? Finally, generate detailed reports. Once you close everything, you want to generate it detailed report. This is a command: report underscore timing, detailed things as I mentioned here. Is it? Okay, so it is for graph-based analysis mode. Earlier was more of a the PB path-based analysis mode. Okay, PBA. It's a GBA. So this is the commands you can use it to generate detailed reports. Okay, graph-based designs. Great. So then once we are done, if you want to save it and future reference or opening again, fix and change it, save the session. This is the command. So save underscore session directory. Okay, all right, and then of course you can quit. Okay, this is a flow. Okay, of course you can check the saved sessions. Okay, and you can switch to the saved sessions and you can exit it. Okay, so what saved session contains is, it contains linked designs, loaded libraries, clocks, timing exceptions, constraints, operating conditions, and I listed everything here. Okay. Okay. Now, we know the flow now, right? So the flow is simple. You load the input files, you update the timing and generate the reports, analyze the reports. As simple as that. Okay, and of course, a lot of commands were listed there. Okay, for a FP prime time. Now let's understand what are the input files required. We already seen it, but again, okay. So this is from Tempus, which is from Cadence, and this is from PrimeTime, which is from Synopsys. The input files are very clearly listed here. Of course, see, both are equally capable. Left side is a little bit more detailed. It's doing more than in the image, doing more than just timing. It's also doing noise and power and so many other things. Right side is not; those things are not captured. Otherwise, they're equally good. So gate level netlist is required. It is obtained generally from design compiler in synthesis flow. It is I'm talking about synthesis after synthesis. Okay, so net parasitics, of course, after extraction we might need net parasitics, in .spf, .gpd, and of course you need libraries .db. .db is that compiled version of the .libs. Okay, so why we compile it? We check for the compiling will help us to check the errors in the .libs, and at runtime is readily consuming it. There is no need for it to compile it again and again. It saves the time, right? Otherwise .lib is enough. Okay. So, and of course, we also need design constraints. Constraints.scdc. What is STC? We'll see it later. Okay. These are the input files required. And what are the output files? The timing reports it generates, and couple of other things it generates. Okay. I'm talking about particularly about timing. So timing reports it generates, and we can save the sessions. This is a library structure. So of course, for prime time, it has got a run.tcl, pt.setup, tcl underscore proc, libs, scripts, and design. Those are so many things. Library structure I'm mentioning here. So this is a summary, the flow, um, and I'm just trying to scratch the surface here, and actual implementation is it will take like many hours. Let's see whether I can continue it later. Thank you very much for your time.